In two-dimensional unit cells, there were 5 types of shapes or 5 types of planar lattices. And these small lattices, they form the part of the plane lattices that repeats to form entire lattice in 2 dimensions. Similarly, in 3 dimensions, the unit cells can be considered as if they are bricks, which are stacked together without leaving any gaps. These cells represent smallest units of space lattices, which repeats in 3 dimensions to produce the space lattice of crystals. To begin with, the bottom of brick shapes will have to be any one of the 5 types of planar lattices or 5 types of planar shapes. Let it be a square bottom. If the bottom will be square and it will be converted into brick, then it will be either a cube or it will be a tetragonal unit cell, because this is a square. So over we can think of these cells, so it will be a cubic cell, cubic unit cell, all sides having squares, but the bottom is square. If the sides are not square, rectangles, then it will give rise to a tetragonal unit cell. When base is square type. So if two-dimensional shapes join so that each corner has 3 edges with angles 90 degree and third is not equal to 90 degree, the result is a monoclinic unit cell. We have the square shapes. This is square, this is square, this is a type of square. But if we consider the angle, here the angle is 90 degree, here the angle is 90, but here this angle is not 90 degree, it is greater than 90 degree. That means this is not a rectangular mesh. This is not a rectangular mesh, but this is rectangular mesh, this is rectangular mesh. If this type of arrangement is there, it will produce a monoclinic unit cell. If all the rectangular bases are there, they may produce orthorhombic mesh, where this rectangular cell is not equal to this rectangular scale and it is not equal to this rectangular scale, because this length, this length, this length, they are not same, but they are mutually perpendicular. So 3 types of rectangles, they join to produce orthorhombic unit cell. If 3 rhombic prisms are placed together, a hexagonal unit cell is produced. So this is one rhombic cell. Then another rhombic cell is like this. Then third type of rhombic cell is like this. This is third type. So it becomes a hexagonal net. 3 rhombic cells joined together, leaving no gap between them, produces a hexagonal unit cell. But this angle should be 90 degree. If bases form parallelograms, a triclinic unit cell is produced. These are parallelograms. This is not equal to 60 degree, 90 degree, 120 degree, not equal to 90 degree. Each base is a parallelogram. The triclinic unit cell. Thus, there are 6 unique type of symmetry possible as shown by unit cells, and they correspond to 6 crystal systems. The symmetries of unit cells are the same as the point groups of greatest symmetry in each crystal system. To describe the shape of the unit cells, we give dimensions and angles. The length of unit cell edges and the angles between them together called as unit cell parameters, and are usually designated as A, B, C. These are the axes. Alpha, beta, gamma are the angles between the axes, edges. For primitive unit cell, A, B, C are the magnitude of the vectors relating to the lattice points, and alpha, beta, gamma are the angles between the vectors. So, based upon that, we have 6 types of unit cells corresponding to 6 crystal systems. The following table shows the vectors and the angles between them that generate 6 possible space lattices. Magnitude of vectors TA, TB, TC. Then this is the angle between TA, TB and TC, unit cell type and the lattice. If TA is not equal to TB is not equal to TC, and all angles are general, not 90 degree, it will be triclinic. Unit cell will be triclinic type, lattice will be triclinic. If TA is not equal to TB, but TB is equal to TC, one angle is general, others 90 degree. This is TA is not equal to TB is not equal to TC. This is not equal to TC. And one angle is general, the others are 90 degree. It will be a monoclinic shape. Shape will be monoclinic type and lattice will be monoclinic lattice. If TA is equal to TB is equal to TC, TA is equal to TB is not equal to TC, and these represent the horizontal axis, this is vertical axis, and TA, TB is 120 degree, TA, TC, TB, TC, they are 90 degree. It will be hexagonal prism, and the space lattice is hexagonal space lattice. If TA is not equal to TB is not equal to TC, all angles are 90 degree, it will be orthorhombic prism and space orthorhombic lattice. TA is equal to TB is not equal to TC, all angles 90 degree, it will be tetragonal prism. TB is equal to horizontal axis. TA, TB, TB, they are all equal 90 degree, it will be cubic lattice. So this is cube. A is equal to B is equal to C, all are 90 degree angles. So this is a cubic lattice. A is equal to B, or it can be designated as A1 is equal to A2 is not equal to C. So this is tetragonal prism. And here in case of orthorhombic, A is not equal to B is not equal to C, and they are 90 degrees to each other. In hexagonal, A1 is equal to A2 is equal to A3. The horizontal axes are equal. A is equal to B means it is A1 is equal to A2 is equal to A3. They are at 120 degree angle to each other, and they are perpendicular to C. So this will give rise to hexagonal prism. And in case of monoclinic, A angle C is not equal to 90 degree. It is greater than 90 degree. That's why A axis is found to be inclined to the front. And B and C, they are not equal, but they are anterior to each other. Also, A and B, they are 90 degree to each other, but A and C, they are not equal to 90 degree. In the case of triclinic, A is not equal to B is not equal to C, and the angles are not 90 degree. This is triclinic. So these are the 6 types of unit cells corresponding to 6 crystal systems are possible in nature, and the entire crystal kingdom of the Indal crystal kingdom is classified into these 6 crystal systems. Then let us discuss. So these are the primitive unit cells that we discussed. Now let us discuss cells with extra lattice points. The 3-dimensional lattices or the space lattices, which represent mathematical concept involving arrangement of atoms molecules in regular manner in form of array of points. Space lattice is simply the array of points arranged in 3 dimension. So this is the type of arrangement. This is type of arrangement. So this is the space lattice. Points, arrangement of points in space. Thus, this arrangement of lattice points, which gives rise to 3-dimensional lattice, they can be produced or they can be thought of to have been produced by layers of 2-dimensional lattices or plane lattices, which are stacked on top of each other in a regular or evenly spaced manner. In this stacking, if this stacking becomes random, there results no symmetry. If the stacking of layers becomes such that distance between layers equals to distance between points in layers, there results a cubic lattice. The smallest unit of such lattice that repeats in 3 dimensions to produce the space lattice is called the unit cell. If we take into account the cubic unit cell in cubic space lattice, the contribution of each cell is equal to 1 lattice point, because this is a cubic lattice, cubic unit cell. So at this point we can imagine 3 others to be united. So this point will be shared by 4 unit cells, and at the top of it there will be 4 unit cells. So this corner will be sharing 8 unit cells. So this atom will be shared by 8 unit cells. So contribution of each corner of a cubic unit cell is 1 by 8. So total contribution of 8 points in a cubic lattice will be 8 into 1 by 8, that will be 1. So the contribution of a primitive cubic unit cell will be 1 atom, because each corner of the unit is shared with 8 unit cells, for which each corner has 1 by 8 contribution, and for the total 8 corners it contributes 1 lattice point. The unit cells which have 1 lattice point are thus designated as primitive and are represented by P. So this is primitive unit cell, because these corners are found to be shared with 8 unit cells. So for unit cell the contribution is 1 lattice point. That's why the unit cell which contributes 1 lattice point, that is called primitive unit cell. So this is the unit cell which is being shared. This point is being shared by this unit cell, this unit cell, this unit cell, this. This is in one plane. Above it there are also 4. So this will be contributed by, this will be joined by 8 unit cell. That's why its contribution is 1 by 8. And if you take into account all the 8 corners of this unit cell, the contribution will be 1 by 8 into 8, that will be 1 lattice point. If stacking of square lattices is such that the distance between adjacent layers is half the distance between the points in each individual layer, there occurs offsetting of each layer from ones that are above and that are below. So, the lattice points of first, third, fifth and so on, the layers are directly above and above each other. This results in a cubic arrangement of lattice points. The lattice points in second, fourth, sixth and so on layers lie exactly in the center of the cube. This gives rise to body centered cubic lattice, which is called I. So, if this is the type of arrangement, we have a layer halfway between these two. In this type of arrangement, we will get a body center lattice. So, it's here the contribution of the unit cell will be, the corners will be 1 unit plus center 1 unit, will be 2 lattice points. In case of body center unit cell, there are 2 lattice points designated by I. If there occurs a stacking of diamond lattices to produce an orthorhombic unit cell, all angles 90 degree but sides of different lengths, it results with extra lattice points in 2 opposite faces. The resulting cell is end centered and designated as by A or B or C, depending upon the location of the extra lattice point, whether it is with respect to crystallographic axis A, B or C. So, this is C. This lattice point is located on the face, on the opposite horizontal faces. So, this is end centered. So, what is the contribution of end center space lattice? These corners are having this much contribution and this one is having, above it there will be one, below it there will be another unit cell. So, half into 2, this will be 1. So, total it will be 1 plus 1, that will be 2. 2 lattice points for end center. For end center 2 lattice points, for body center 2 lattice points, for primitive 1 lattice point, and for face center, if all the faces are taken together, the faces will have 3 lattice points and primitive will have 1 lattice point, that there will be 4 lattice points. Then we can sum up. All these lattice points can be grouped into 14 types of Draveis lattices. If you take into account primitive, body center, face center, end center, and if you consider the crystallographic or the systems, we can consider that there are 14 space lattices possible, which are called as Draveis space lattices. In case of primitive, we have cubic primitive, which is designated as 23p, tetragonal it is designated 4p, orthorhombic it is 222p, and in hexagonal it will be 6p or 6c. So, these are the primitive unit cells. There are 6 corners on the top, 6 corners on the bottom. Each corner is shared by 6 unit cells, hence the contribution of each corner is 1 by 6 in case of hexagonal. So, there are 12 corners, so contribution will be 2 points per unit hexagonal cell. As per convention, primitive cell contains one lattice point. So 3 comes from division of hexagon, comes from the division of hexagonal cell as 3 parallelogram columns join. But generally it is considered to be 1 hexagonal net contribution, either it is considered to be 1 or it is considered to be 3. So this is about the primitive. So this is cubic primitive, tetragonal primitive, orthogonal primitive, hexagonal primitive. Then we have the monoclinic primitive and triclinic primitive. 2p is representing monoclinic primitive, 1p is representing triclinic primitive. So 6 numbers of primitive cells. Then body centered. In cubic we have one body centered represented by 23i. In tetragonal we have one body centered, it is represented 4i. Orthorhombic it is 2i, and in monoclinic it is 2i. So there are total body centered. There are 4 total body centered cubic body centered lattices. If we take on the face centered, it is only in cubic 23f, and it is there is another face centered lattice, that is 222f in orthorhombic system. So total 2 face centered cubic lattices. So if we take into end centered, it will be there in orthorhombic. It may be 222a, it may be 222b, or it may be 222c, and their contribution will be 2 lattice points end centered. If it is rhombohedral, it has contribution 1 lattice point. So thus there are 3 cubic lattices, 2 tetragonal lattices, 1 triclinic lattices, 4 orthorhombic lattices, 2 monoclinic lattices, 1 hexagonal lattices, total 14 Bravais lattices. This is total 14 Bravais lattices. So these 14 Bravais lattices along with 32 point groups in combination with 20 rotational axis of symmetry operations and 5 planes involving glide deflection all together account for 230 space groups which are possible in the entire crystals found in nature. Thank you all for giving a patient hearing to my talk.